Good morning, students. Today we shall be doing Gauss law. Gauss law states the surface integral of an electrostatic field produced by a source over any closed surface enclosing a volume V in vacuum is 1 by epsilon 0 times the total charge Q enclosed confined in S. Now see how does it look like. Suppose the volume enclosed is V and this is the surface, right? And this surface is a closed surface. So suppose there is some charge here. The charge may be distributed or may be confined to a point, it doesn't matter, but the total charge is Q enclosed. So the mathematical statement should go like this: the surface integral E dot ds, E is the electrostatic field and ds is the elemental surface here. This is the ds vector, and suppose the electrostatic field at this point is like this E. Suppose you can also take a surface here and the electrostatic field might be like this. It doesn't matter at all, right? We should take a dot product. So this is the surface integral over the closed surface S. You should put an S like this, that means surface integral. That is equal to the total charge enclosed within the surface divided by epsilon 0. So that is the mathematical statement for Gauss law. Suppose you are here, the electrostatic field may be parallel to the surface, elemental surface area, or it may be at an angle. It doesn't matter. The dot product will manage that angle. So this will be E ds cos theta is equals to Q enclosed over epsilon 0. Now few things needs to be taken care of. What is this thing? This E dot ds. E dot ds, this is the total flux over the closed surface S. Okay. Few things to be noted. Let's note them one by one. Point number 1. This Gauss law, this can be used as an alternative procedure for calculating electric fields. We have calculated electric fields using Coulomb's law. This Gauss law can be used as an alternative procedure, but there are conditions, the symmetry is needed. So I'm coming to that. So point number 2 is, these are important notes, right? So point number 2 is, it is based on inverse square law of electric forces between point charges. So that is Coulomb's law. The thing is, you can deduce Coulomb's law from Gauss law. That is also a method. I shall do this. And there is another important point. It is convenient for calculating electric fields for highly symmetric systems. Or symmetric charge distribution. Now, if you see, there are few points which needs to be taken care of, which to be dealt with first to understand this Gauss law. First important point is this flux. This word, this flux. What is a flux? And the second important point is this symmetry. These two things should be taken care of separately before going into the further discussion of Gauss law. Okay. Now we shall go into electric flux. Now what's an electric flux or an electrostatic flux? Electrostatic flux is a measure of electrostatic field through a given surface. Okay. Now let's take a constant electrostatic field first. First, case 1, we take a case 1 constant electrostatic field. Now what is a constant electrostatic field? Now if the electrostatic field do not vary with space, if anything do not vary with space, so that is a constant field. So if the field or if the electrostatic field do not vary with space, it is a constant electrostatic field. So let's draw it. Suppose these are constant fields coming from one side, from the left to right. And you see, as we go from left to right, there is no change in the direction as well as the magnitude. So each point if you mark the field as red, the magnitude will be like this. Okay, each point, if you mark the field, the magnitude will be like this. The length of the arrow is same, as well as the direction of the arrow is also same. Now if you take a surface which is perpendicular to this field, let's take a surface. Suppose this blue is a surface which is perpendicular to this field. Now what is the amount of the electric field passing through? This is also the electric field lines. If the area of this surface is A, suppose this area is A, suppose this area is A, and the electric field is E, so what is the amount of electric fields passing through this area? So the amount of electric field passing through this area, or flux phi E, is E times A. Now what is this area? Is the area is a scalar quantity or a vector quantity? Now as far as this area is concerned in 3 dimensions, area in 3 dimension is a vector quantity. Then the immediate question comes, what's the direction of the area? Just do one thing, just traverse this area in an anti-clockwise fashion, okay, and then this area, the direction will be, if you rotate a right-handed screw in the same direction, the direction of this area will be in this direction. This is area vector. So in this case, the electric field as well as the area is parallel to each other, so the angle between them is 0. So you can write this as E vector dot A vector. Now consider another case where this area is at an angle, right? So this area is at an angle. Take few fields like this, or what we can do is we can take the area here itself. Suppose the area is like this. Take another area. Suppose the bottom is the same, and let's try another area. Right. So this is the area which is at an angle theta with the field. So how do you measure the direction? So naturally the angle will, the area vector will be perpendicular to this area, right? So perpendicular to this area, and this is the new area vector. Now in this case the electric field doesn't change. So what's this angle between the initial area and the new area? Right. The magnitude of the area is the same because we have rotated the same area by an angle theta. So this angle is theta. Okay. Now the direction of the electric fields remains the same, right? So the direction of the electric field remains the same. Okay. So what's the angle between the electric field and the new area? Naturally that will be also theta, because if you have rotated the initial area by an angle theta, the direction, the amount by which the new area is rotated from the electric field is also theta. So what's the flux passing through this new area? See, if you have rotated by an angle theta, the amount of flux is less. So that means you can think like this: what is the projection of this area parallel to this field, or what is the projection of this area parallel to this field? So you can think it like this: an area which is projected parallel to this field is like this. Right? Or sorry, let's use straight lines, suppose, or use purple. Suppose this one. Okay, the projection will be draw it on the initial area itself. Right, and make it. So what's the projected area? The projected area will be this green one. This green one is this projected area. Suppose this is A prime. So what will be A prime? Naturally it will be A cosine of theta. So the amount of flux, passing through A when it is at an angle theta with the field is the same amount of flux passing through A prime. So now phi E prime is E A prime, or equals to E A cos theta, or E dot A. So this E dot A is the general expression for the electric field, or a constant electric field passing through a flat surface which is at an angle theta with the electric field. Now we can easily say that, so this is case 2. This is case 2. Now we can easily say that if theta is equal to 0, the maximum flux goes through this area, and if theta is equal to 90 degree, when theta becomes 90, well, when this area is completely, or the area vector is perpendicular to the field, or you can say it like this, or let me draw this, let me draw it in purple, or let me draw it in sky. So now this area is, suppose this is A double prime. Now A double prime, the flux through A double prime is completely 0. So you can write it here in small case 3, flux through A double prime is 0. See, nothing is going in. So what's the area vector? it is perpendicular. This is the A double prime vector. So phi E double prime is equals to E dot A double prime vector. So that is E A cos 90 degree, that is equal to 0. So this is case 3. So first case is it is at a general angle, and the second case is it is at an angle theta, and the third case is it is completely flat, or the area vector is perpendicular to the field. So let me point these arrows, right? So this is case case 1. Let me take yellow will be bright. This area is case 1, this area is case 2, and this area is case 3. Fine. Now let's go to a field which is not constant, and we will test the electric flux through those fields. Now we shall be doing with spherically symmetric electrostatic flux. Now what is spherically symmetric electrostatic flux? Rather, what is spherical symmetry? See, first realize it physically, then we will go into the symmetry. We have to deal symmetry separately, but try to realize this. Suppose you have a sphere and a charge is located at the center of the sphere. Suppose there is a charge plus q, and if you take a sphere, any sphere, taking this point charge as center, suppose if this radius is smaller, you see two spheres, two concentric spheres. If the radius is smaller and you have an area dA, you see this area dA, the amount of flux passing through this area is E dot dA, right? So phi E for this small sphere is, or let's write a differential, E dot dA. Now if we increase the radius by twice and we see the same area projected on the higher sphere, so the increment in the area will be 4 times, because see, what is the area of a sphere? It is area of a sphere is pi 4 pi r square, where r is the radius, right? Now see the area, so area is proportional to the radius square. Now in this case, suppose if you take the whole area of the sphere, the area is, what will be the area? 4 pi r square. And what is this area of this bigger sphere? 4 pi into twice r square, so that is 16 pi r square. So that is 4 times 4 pi r square. So area, the increment in the area is 4 times, right, if the radius is doubled. So that is, the area increases by square of the radius. Now what is spherically symmetric electrostatic flux? Let's understand what is a spherical symmetry. So let's understand this, what is a spherical symmetry. Spherical symmetry, or anything Spherical symmetry is defined as anything, any function which is only dependent on R is spherically symmetric, or other R vector also is spherically symmetric. Fine. Now, if this point charge is plus q, what is the electric field here? What is the electric field here? The distance is r, so E will be 1 by 4 pi epsilon 0 q over r square times r cap, right? R cap is the unit vector radially outward. This is r cap. Here the direction of r cap is in the same direction. This is r cap. Now what will be the electric field here? Can you tell me? Is it large or is it small? Smaller than this. It is smaller. How much smaller? It falls by 1 over r square. Why? Because it is by Coulomb's law. It is 1 over r square. So the electric field E here will be 1 by 4 pi epsilon 0 q by twice r whole square times r cap. So that is 1 by 4 pi epsilon 0 q by 4 r square r cap. Now see, if you see the function, right? So if you see the function at any surface, E is a function of r only, right? Well, let me write it clearly, then you will understand. Let me write it first. E is 1 by 4 pi epsilon 0 q over r square r cap for any sphere which has radius r. So this is a function of r times r cap. There is nothing else in it. If any function looks like this, it is a spherically symmetric field. So this is a spherically symmetric field. So what is a symmetry? Let's get a very small what shall I say? Let's discuss a symmetry in a nutshell. Then we'll go into further details how this flux is calculated. So symmetry in a nutshell. Let's define it. A symmetry of a physical system is a physical or a mathematical feature of the system that is preserved or remain unchanged rather invariant, remains invariant under some transformation. Let's see the former case first, then you will be able to understand what it is. Suppose you have the sphere here. Let's take it a little smaller. First, now see the sphere. Now if I suppose I am standing at any position, and if I rotate the sphere, right, if I rotate the sphere like this, do you feel any change in the system? Suppose if I rotate the sphere like this, do you feel any change in the system? Or let me analyze it like this. Suppose I am standing here. Suppose this is the surface of the earth. Or you stand here. What do you feel? You are standing on the top of a surface, right? Or you can think it like this. Suppose you are moving on a ship over the deep sea and there is no land anywhere. If you don't see that the ship is moving, you are standing on the deck, suppose you don't realize that the ship is moving. If it had moved 10 kilometers in any direction, it hardly matters that whether the ship is moved 10 kilometers or has not moved 10 kilometers. Suppose the ship is from here to here. Suppose the ship is moving from here to here, right, and now you are here. So when you are standing here, you see that you are in a deep sea and you are above a deep sea, and if you are standing here, you also see you are above a deep sea. So you have moved continuously from this position to this position, and you will feel that you are radially at the same position as far as this sphere is concerned. Fine. You are at a distance r from the center. You are here also at a distance r from the center. This is a continuous symmetry. Why? Because you have moved from one position to the other continuously and you have not seen any change. Let's take a circle like structure, then we'll be able to understand it a little better. Suppose this is a small circle and let's the center of the circle is here. This is a sphere. So this is a sphere and this is a circle, right? This is a circle. Now if you are here, if you are at this position, and there is nothing around, this only circle and you are at this position, and if you make a transformation on the circle, that on the circle means circle is what? Circle is a locus of a point. It is a locus of a point. Circle is the definition of the circle is locus of a point which has a fixed distance from a fixed point. Say this fixed point is O. Okay. So the distance from this fixed point to this point is constant. Now if you are here, you are changing your position. But if there is nothing other than this circle, then whether you are here or here, it doesn't matter at all. Okay? You will not be able to identify that any changes have happened. To try to realize this, suppose there is no stick, there is nothing, only this point, and you are standing here. So if you are standing here, or you are standing here, or you are standing here, or you are standing here, you will see the distance from the point to from you is fixed. So there is no change. So the transformation is the movement on the circle, and the system, that means what you are saying, this center, the center point, you are looking at this point, this system is invariant under this transformation if you move along the circle. So since you are moving on the circle continuously, this is called a continuous symmetry. This is also a continuous symmetry. Acha, as opposed to this continuous symmetry, we have another symmetry, but we will not go into the details of symmetry, but let me tell you a little bit, then you will be able to understand. Let's take a square like structure, very small square, and suppose this is a square like structure, and suppose you are standing at the middle, or you are standing here. Now if you rotate the square, this is all about the previous is continuous symmetry. Let's see this. Now if you rotate the square, suppose this position, there are 4 charges located, Q, 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 plus Q, straight. Suppose there are charges located, or if even there is no charge, then it's also true. Let's leave the charge first. Suppose there is a square. Now if you rotate the square by 90 degrees about the center, it's like this. Let's take axis like this. This is one axis and this is the other axis, and suppose this is X and this is Y. So after 90 degrees, 180 degree, 270 degree or 360 degree, means a complete rotation, there is no change. There is no change in the system as far as you are concerned. But you are not moving it continuously, right? You are moving it discretely. Only these values, 90, 180, 270, 360. So this is called a discrete symmetry. This is called a discrete symmetry. you will need this in electrostatics as well. Suppose this is a discrete symmetry. Let's say if I give you a problem, suppose let's go to the next frame. Suppose you have a hexagon like structure. Right. Now suppose if you are asked how many folds of symmetry does this hexagon have? So if you rotate this hexagon, so this is the question. So what's the answer? So if you rotate the hexagon about the center O by 60 degree, 120 degree, 180 degrees, that is in multiples of 60, then 240 degrees, 300 degrees, 360 degree, then there is no change in the system as far as this person is standing, as far as you are concerned, right? And these rotations are the transformations. Are the transformations. So this hexagon has a 6-fold discrete symmetry. Now if you are asked another question, suppose another question, I give you a question. Let me draw a small cylinder. Suppose this is the axis of the cylinder, and suppose this is the axis of the cylinder, and right. Now suppose this is the what shall I call, this is the z axis, and suppose these are the this is one axis, this is x, this is y. Now if you are asked what is the symmetry about the axis of the cylinder. Now you are standing here, suppose, and what you do is you rotate this cylinder about the axis. So even if you rotate at a very small angle, the cylinder doesn't change. You will not see, suppose there is a point here, suppose cylinder is polished, so this point will come here, right? This point will come here, but the cylinder will, if the cylinder is polished, so this is the solution. If the cylinder is polished, you shall not see any change. If the cylinder is rotated about the z-axis, so this has continuous symmetry. About the z-axis. About the axis of the cylinder. Okay. This is symmetry in a nutshell. So what shall I do is, we go into Gauss law and we will try to figure out what's the advantage, what's the disadvantage. Let's go to the first frame. As I told you, the Gauss law is the surface integral of an electrostatic field produced by a source over any closed surface enclosing the volume V in vacuum is 1 by epsilon times the total charge Q enclosed confined within the S. So there are three notes I told you. It can be used as an alternative method in calculating the electric field. So this we shall do. We can find the Coulomb field using Gauss law, and this is based on the inverse square law. That means if the Coulomb field is true, the Gauss law will be true, and also we will need very highly symmetric surfaces to find these integrals E dot ds, right? So let me go into the Gauss law in my next lecture.